Okay, fine. Good morning, all of you. I hope my screen contents are visible to you. Whatever I'm doing on visible to you, any one of you please reply in chat box. Whether whatever I'm doing, is it visible to you? Yeah, Alvin, my screen is visible to you. Please reply. Okay, I think fine. So I'll start now. Okay, good morning to you. Let us start with introduction to Verilog HDL. HDL stands for Hardware Description Language, and that is used to describe the hardware. For example, a computer or a component can be described by using HDL. So it can be described by using various levels. One of the level is switch level, other level is gate level, and third one is register transfer level, that is known as RTL. Now let's see the application areas of HDL. We can use it for system specifications at the behavioral level, and that can be a combination of hardware and software. It can be partitioned into hardware and software. In hardware specification, the design can include either ASIC, that is application specific integrated circuit, or FPGA, which is nothing but field programmable gate array, or it can be implemented by using PLD, that is programmable logic devices, or it may be parts which can be used. And finally, it can be implemented on boards and systems, whereas part of the system or design can be implemented by using software, and we can specify the software specifications, and ultimately it's a combination of hardware, maybe using ASIC, FPGA or CPLD, and the software which is required to implement that design can be used to specify the system. Basic limitations of hardware description languages. It can be used to describe only the digital systems. It cannot be used to describe the analog systems. So this is the limitation of HDL. Now let's move on to the abstraction levels in HDL. One of the level is behavioral level. Second level is register transfer level. Third one is gate level. And the next one is layout or VLSI. So our focus is on the first three levels, that is behavioral, register transfer level, and gate level. Now let's see the main language concepts. There is a concurrency in the design, and the design can be described by using the structural level of modeling. That is, as shown in this figure, you can guess what type of design this is. This is a combinational logic design, and that is it's making use of these components U1, U2, and U3. So this U1, U2, and U3 will be a combinational logic or gates. So here the inputs are A, B, and C in, and the output is sum and carry. So you can say that this is actually adder, and A, B, and C in, they are the inputs. So you can say that this is a full adder design because this is having carry input, and A and B are the inputs. So U1 and U2 here, they are the half adders. So we can say that full adder is designed here by using, already shown here by using two half adders. So here half adders, U1 and U2, they are half adders, and U3 is the gate which is used to generate the carry. So these are the components, several of components, and there is a requirement of wire to interconnect the output of one of the component to the input of another component, or output of say component to the final output. We can say the signal output, that is sum and carry. It includes, HDL includes the procedural statements, that is section of codes, they are executed in the straight line flow, that is execution will be in this way, and this shows the timing behavior of the design when it is done in HDL. Now let's see why use HDL. When HDL was first developed, most logic simulators operated on netlists. The netlist is nothing but the list of gates and how they are connected. It gives the information about list of gates and how they are connected. And is a natural representation of a digital logic circuit. It's not a very convenient way to express design, simulate, and debug. The reason why HDL is used is because it is text-based and it allows simulation before building a circuit. So without ever touching the hardware, you can check the functionality of the circuit in simulation. It can be compiled or synthesized into logic circuits, and it is much easier to write the test benches in HDL. One more reason why HDL is used is because it gives the more abstract models of the circuit, and it provides you easier to write, and you can do the simulation faster. It is more flexible language. It provides sequencing because it allows both the model and the test base to be written together. That is the success of Verilog. So let's see now how HDL is used. Design is written in HDL and then it is simulated to check the functionality, and then it is synthesized or netlist is generated. Then static timing analysis is done to check the timing. There are two major hardware description languages. One is HDL, stands for very high speed integrated circuit hardware description language, and second one is Verilog HDL. So the VLSI systems or the systems which makes use of the devices like FPGA or ASIC or CPLD, they are designed in part using one of these two languages, that is either VHDL or Verilog. So it combines the structural and behavioral modeling styles. So we are concerned with the Verilog HDL. So our focus is on Verilog HDL. So Verilog HDL is the hardware description language which is introduced in 1985 by Gateway Design Systems, and now it is a part of Cadence Design Systems. It became an IEEE standard in 1995, and its syntax is based on C programming language. So those who are familiar with C programming language, it is convenient or easier for them to understand the Verilog language. Now let's move to the design methodology. The design methodology includes HDL specification, that is structure and function of a design is formulated, and it contains two parts, that is simulation and synthesis. In simulation, verification is done, that is it is tested whether the design behaves as required. So in functional, IO behavior is tested. Then register level, architectural level or logic level gates, transistor level electrical and timing waveform behavior is tested using simulation. Whereas in synthesis, it is the design which is simulated and then tested in simulation is mapped to the implementation that is on the actual device. There are two main components of Verilog. One is behavior, that is concurrent event triggered processes, and second one is structure, that is wires and interconnection. Structural and behavioral model. Let us see what are the peculiarities. Structural Verilog in this module instances and their interconnections by wires only. And in behavioral, use of REGs, time delays, arithmetic expressions, procedural assignments, and other control flow structures they are used, like if else, else if, and so on. Now let's move on to the concept of Verilog module. Let me check whether anybody is waiting for there to join. I think I need to admit them. Fine. Well, I think nobody is waiting there in the lobby. So I hope let us continue. Okay, fine. Somebody is saying that switch off the webcam. I will switch it off. I will turn off my camera. Fine. So now let's continue. Fine. So let's see the concept of Verilog module. In Verilog, the basic unit of hardware is called a module, and modules cannot contain definitions of other modules. Whereas a module can, however, instantiate another module. That allows creation of hierarchy in Verilog description. Now let's see the syntax of module definition. The syntax of module definition is module, module name, list of ports, and then next input output declarations, local net declarations, parallel statements, and end module. So as far as this module syntax is concerned, module, end module, these are the keywords. Module name, list of ports, they are the identifiers, and input output declarations. They are also containing the keywords like input and output, and local net declarations and parallel statements. So this is the syntax of module definition. Now let's see the example of module